A very important property of transition metals is to form complexes. Complexes or coordination compounds are found in many places on Earth's surface. Every living system includes many coordination compounds. They are also important components of everyday products like cleansing materials, medicines, inks and paints. Complexes are formed by bonding between metal and ligands. This unit, namely metal-ligand bonding in transition metal complexes, is very important to understand formation of complexes. Today, we are going to discuss valence bond theory for coordination compounds, limitations of valence bond theory, crystal field theory, important features of crystal field theory, splitting of d orbitals in octahedral complexes, and splitting of d orbitals in tetragonal and square planar complexes. Bonding theories for coordination compounds should be able to account for structural features, colors and magnetic properties. Valence bond theory provided the first detailed explanation of the electronic structure of complexes. This explanation is essentially an extension of the view of covalent bonding. According to this view, a covalent bond is formed by the overlap of two orbitals, one from each bonding atom. In the usual covalent bond formation, each orbital originally holds one electron, and after the orbitals overlap, a bond is formed that holds two electrons. In the formation of coordinate covalent bond in a complex, however, a ligand orbital containing two electrons overlaps an unoccupied orbital on the metal atom. Here you can see, in the usual case, each overlapping orbital contains one electron and a covalent bond is formed. When a coordinate covalent bond forms, one orbital contains a lone pair of electrons and it overlaps with an empty orbital, and here is the coordinate bond formation. The valence bond theory was fairly successful in explaining qualitatively the geometry and magnetic behavior of the complexes. But there are some limitations of valence bond theory. It does not explain the color exhibited by coordination compounds, and the origin of their absorption spectra could not be explained by valence bond theory. Valence bond theory does not give a quantitative interpretation of the thermodynamic or kinetic stabilities of coordination compounds. It does not explain as to why should certain ligands form high spin while others low spin complexes. The changes in energies of the metal orbitals on the formation of complex are difficult to calculate mathematically by using valence bond theory. It does not make exact predictions regarding the tetrahedral and square planar structures of four coordinated complexes. Sometimes the same metal ion assumes different geometry when formation of complex ion takes place. The theory is unable to explain why at one time the electrons are rearranged against the Hund's rule while at the other times the electronic configuration is not disturbed. It does not distinguish between weak and strong ligands. It does not explain the temperature dependence of magnetic properties. It assumes that all d orbitals in a complex are equal in energy. Too much stress has been laid on the metal ion while the importance of ligands is not properly stressed. Valence bond theory cannot explain reaction rates and mechanism of reactions. Valence bond theory cannot explain why square planar complexes of Cu2 plus ion, that is D9 system, like CuNH3 2 plus are not reducing agents like inner orbital octahedral complexes of cobalt 2 plus, that is D7 system. Although in both the cases promotion of a non-bonding d electron to some higher energy level is required. The valence bond theory represents the ligand metal bond as covalent with an electron pair shared between the metal and the ligand donor atom. This theory is frequently used, but it is not adequate to explain properties of complexes such as color and magnetism. It is firmly established that both the color and magnetic properties of transition metal complexes are due to their possessing d orbital electrons. Therefore, there must be a quantitative connection between spectra and magnetic moment. Unfortunately, this connection is not revealed by valence bond theory, which does not consider the splitting of d orbitals of the central metal ion, and consequently these properties, that is magnetic and spectral properties, could not be explained by this theory. Currently, the bonding in coordination complexes is usually described by crystal field theory. This theory accounts for more satisfactory explanation for the properties of complexes, especially color and magnetism. Crystal field theory was proposed by H. Bethe in 1929 and Van Vleck in 1932 and was originally applied to ionic crystals to explain their optical properties and is therefore called crystal field theory. However, this theory was applied to study of coordination compounds in 1950s. The crystal field theory concentrates on the splitting of d orbitals of the transition metal atoms into groups as a result of electrostatic interactions between the ligands and the electrons in the unhybridized orbitals of the transition metal atom. The theory can be used to understand, interpret and predict the magnetic behavior, color and some structures of the coordination complexes. This theory regards the ligand atoms of ionic ligands such as I-, Cl- or Cn- as negative point charges. And if the ligands are neutral molecules, these are regarded as point dipoles or simply dipoles. Since such ligands are dipolar like ammonia and water molecules. Here you can see the examples of two dipolar ligands. Here is the positive end and this is the negative end of a dipole molecule like ammonia. Similarly, here is the positive end and this is the negative end of the dipolar molecule H2O. Here it should be clearly understood that to regard the ligand atoms as simply points is a sheer formalism which is devoid of physical meaning. Actually, the ligand atoms are not points but are bodies with about the same size and structure as the metal atom itself. Thus, it can be said that crystal field theory regards the ligand atoms as negative point charges or dipoles aligned with their most negative regions towards the central metal ion. Such ligands approach the central metal ion with negative poles closest to the central metal ion. Actually, even if the ligands are not negatively charged, that is, if they are neutral ligands, they are polarized by the positive charge of the cation and thus appear negatively charged. Thus, in the complexes having neutral molecules as ligands, the central metal ion is surrounded by dipoles. This considers only those complexes which are having a central metal ion surrounded by the ionic or dipolar ligands and with partially filled d orbitals. The theory also considers the effect of ligands on the energies of the d orbitals of the central metal cation or atom. Now we have to discuss the important features of crystal field theory. CFT regards a complex as a combination of central ion surrounded by other ions or molecules with electrical dipoles, that is ligands. It considers these ligands as point charges or as point dipoles. In its simplest treatment, crystal field theory does not consider covalent bonding in complexes, but the bonding between the metal cation and ligands arises from the electrostatic attractions between the nucleus of the metal cation and the partial negative charge invariably present on the ligands. The interaction between the electrons of cation and those of the ligands is entirely repulsive. It is these repulsive forces that are responsible for the splitting of the d orbitals of the metal ion. The bonds between the metal and the surrounding ligands are thus purely ionic. The crystal field theory does not provide for electrons to enter the metal orbitals. Thus, the metal ion and the ligands do not mix their orbitals or share electrons. That is, it does not consider any orbital overlap. Crystal field theory gives a representation of bonding that is purely an electrostatic or Coulombic interaction between positively charged cation and negatively charged anions or dipole molecules which act as ligands. Complexes are thus presumed to form when centrally situated cations electrically attract ligands which may be either anions or dipole molecules. The attraction between the cations and ligands is because the cations are positively charged and the anions are negatively charged, and the dipole molecules as well can offer their negatively incremented end for such electrostatic attractions. The arrangement of ligands around the central metal ion or atom is such that the repulsions between these negative points or dipoles is minimum. Interactions between positively charged nucleus of the central metal ion or atom and the negatively charged ligands are of two types. The attractive forces arise due to the positive metal ion and the negatively charged ligands or the negative end of apolar neutral molecules. These attractive forces bind the ligands to the metal ion. The bonds between the metal and the surrounding ligands are purely ionic. This theory does not consider any orbital overlapping. The repulsive forces arise between the lone pairs on the ligands and electrons in the d orbitals of the metal or atom. The crystal field theory mainly focuses on these repulsive forces. These forces are responsible for causing a considerable effect on the relative energies of the d orbitals of the central metal ion or atom. In a free transition metal or ion, there are 5 d orbitals which are designated as dxy, dxz, dyz, dx square minus y square and dz square. You can see these 5 orbitals. It is dx square minus y square, dz square, dxy, dxz and dyz orbitals. The 5 d orbitals are divided into 2 sets depending on the nature of their orientation in the space. The 3 d orbitals dxy, dyz and dxz which orient in the regions between the coordinate axes are designated as T2g orbitals. T2g orbitals are threefold degenerate. These are non-axial orbitals. You can see these 3 T2g orbitals here. In dxy orbitals, lobes of the d orbitals are lying between the x and y axis. In dxz orbitals, lobes of the orbitals are lying in between x and z axis, and in dyz orbitals, lobes of the orbitals are lying in between y and z axis. The other 2 orbitals, that is dx square minus y square and dz square, which orient along the axis, are called Eg orbitals. Eg orbitals are twofold degenerate. These are also called axial orbitals. Here you can see in dx square minus y square, the lobes of the orbitals are pointing towards x and y axis, and in dz square orbitals, lobes of the orbital are pointing towards z axis. The names T2G and EG are derived from spectroscopic terms. In a free transition metal ion or atom, all the 5 d orbitals have same energy, that is, they are degenerate. However, when the ligands approach the central metal ion or atom, the electrons of the d orbitals of the central metal ion or atom are repelled by lone pairs of the ligands. As a result of these interactions, the degeneracy of d orbitals of the metal ion is lost depending on the orientation of ligands in space. The d orbitals split into two sets of orbitals having different energies. This is called crystal field splitting. It is the basis of crystal field theory. The extent of splitting depends on the number of ligands and their position around the metal atom or ion. The splitting is different in different structures with different coordination numbers. Now, we are going to discuss the splitting of d orbitals in octahedral complexes. Let us consider an octahedral complex Ml6N+, in which the central metal ion is placed at the center of the octahedron and is surrounded by 6 ligands which reside at the 6 corners of the octahedron. You can see here, this is the metal ion and 6 ligands are approaching the octahedron. The electrons in d orbitals of the metal cation are repelled by negative point charge or by the negative end of the dipole of the ligands. This repulsion increases the energy of all the 5 d orbitals. If all the ligands approaching the metal cation are at an equal distance from each of the d orbitals, that is, the ligand field is spherically symmetrical, the energy of each of the 5 d orbitals increases by the same amount. That is, all the d orbitals remain degenerate, although they possess higher energy. However, it is only hypothetical situation. Now notice that the lobes of dz square and dx square minus y square orbitals point towards the charges, that is, ligands. You can see the lobes of dz square are pointing towards these ligands and lobes of dx square minus y square are pointing towards these ligands. And the lobes of dxy, dyz and dxz orbitals point between the charges or ligands. In dxy, the lobes of the orbitals point in between these two ligands. The lobes of dyz orbitals are pointing in between these ligands and the lobes of dxz orbitals are also pointing between the ligands. Since the lobes of two Eg orbitals lie in the path of approaching ligands, the electrons in these orbitals experience greater force of repulsion than those in T2G orbitals, whose lobes are directed in space between the path of the ligands, that is, energy of Eg orbitals is increased while that of T2G orbitals is decreased. Here, the ligands approaching the metal ion in spherical field and all the 5 d orbitals will be degenerate. But the energy of the 2 orbitals of Eg set will be increased, that is, the energy of dz square and dx square minus y square orbitals will be increased and the energy of dxy, dyz and dxz orbitals which comes into the group T2G will be decreased. An energy difference exists between two sets of orbitals. This energy difference is called crystal field splitting energy and is represented by delta O. The subscript O stands for octahedral. It measures the crystal field strength of the ligands. The crystal field splitting occurs in such a way that average energy of the d orbitals does not change. Thus, 3 orbitals lie at an energy that is 2 by 5 delta O below the average d orbital energy, and 2 d orbitals lie at an energy 3 by 5 delta O above the average energy. The energy gap between T2g and Eg sets is also denoted by 10 dq. Energy of T2g orbitals is 4 dq less than that of hypothetical degenerate d orbitals, and that of Eg orbitals is 6 dq above that of the hypothetical degenerate d orbitals. Thus, T2g set loses an energy equal to 0.4 delta O or 4 dq, while Eg set gains an energy equal to 0.6 delta O or 6 dq. Here you can see that the energy increase of the Eg orbitals and the energy decrease of the T2g orbitals must be balanced relative to the energy of the hypothetical spherical field, and this is also called Berry center. These are 5 degenerate orbitals on the metal ion in spherical octahedral ligand field, and this is the splitting of d orbitals. Now we will discuss the splitting of d orbitals in tetragonal and square planar complexes. If two trans ligands lying on the z-axis of an octahedron moves away from the central cation so that their distance from metal cation is slightly greater than it is for other 4 ligands lying in the xy plane, we get a tetragonally distorted octahedron, and such a structure is called tetragonal structure. XZ plane, that is dxz orbital, and YZ plane, that is dyz orbital, experience less repulsion from the ligands than they do in an octahedral geometry, and those in the xy plane, that is dxy and dx square minus y square orbitals, experience relatively greater repulsion. Consequently, the energy of the orbitals experiencing less repulsion decreases, while that of the orbitals experiencing greater repulsion increases. Here you can note that the dxz and dyz orbitals are degenerate. Thus, under the influence of the ligands in tetragonal complex, the order of energy of various orbitals is dyz equal to dxz, which is less than dxy, which is further less than dz square, and the energy of dx square minus y square is highest. Here you can also see that the energy of the orbitals in xy plane, that is dx square minus y square and dxy, increases, and the energy of the orbitals in yz or xz planes, that is dyz and xz, and also of dz square, decreases. Now we are going to discuss the crystal field splitting of d orbitals of the central metal cation in square planar field. If the two trans ligands on the z axis are completely removed, we get a square planar geometry. This is accompanied by a further rise in the energies of dx square minus y square and dxy orbitals, and a further fall in the energies of dxz, dyz and dz square orbitals. Thus, in square planar geometry, the order of energy of different d orbitals is dyz equal to dzx, which is less than dz square, which is again less than dxy, and dx square minus y square orbital has the highest energy. Here you can see the crystal field splitting of d orbitals in octahedral field, in tetragonal field and in square planar field. In square planar field, the energy of dyz and dxz orbitals further decreases and also the energy of dz square decreases, but the energy of dxy orbitals increase and that of dx square minus y square orbitals also increases. The crystal field splitting in square planar complex is denoted by delta Sp. Here the subscript Sp represents square planar. This delta Sp represents the total square planar splitting from the lowest dxz and dyz pair to the highest dx square minus y square and is given by delta Sp is equal to energy of dx square minus y square minus energy of dxz and dyz. This will be equal to energy of dx square minus y square minus energy of dxy plus energy of dxy minus energy of dz square plus energy of dz square minus energy of dxz and dyz. This will be given as delta 1 plus delta 2 plus delta 3. The value of delta Sp has been found larger than delta O because of the reason that dxz and dyz orbitals interact with only 2 ligands in the square planar complexes, while in the octahedral complexes the interaction takes place with 4 ligands. Delta Sp has been found equal to 1.74 delta O. Therefore, delta Sp will be equal to delta 1 plus delta 2 plus delta 3, which is greater than delta O, and also delta Sp is equal to 1.74 delta O. Note that the crystal field model does not explain the bonding in coordination complexes. It describes only behavior that can be attributed to electrons on the transition metal atom in the coordination complex. So, in the end of this lecture, let us revise what we have learnt today. Today we discussed valence bond theory for coordination compounds, limitations of valence bond theory, crystal field theory, important features of crystal field theory, splitting of d orbitals in octahedral complexes, and splitting of d orbitals in tetragonal and square planar complexes. In next lecture, we will continue the splitting of d orbitals in tetrahedral complexes.